Thank you so much, Dean Armstrong. Some housekeeping rules. Please introduce each other whenever you're in breaks, especially people with expertise different from yours. This is the point of this conference, to be collaborative and to do really good science. And keep all those things in mind. Health inequity are some real issues that we want to grapple with, and maybe this is the audience that will eventually fix all of these problems. So with that, let's get started with our first speaker. Our first speaker for today is Dr. Ben Marlin. He's an associate professor in the Manning College of Information and Computer Sciences at the University of Massachusetts Amherst, where he directs the Robust and Efficient Machine Learning Lab. He was previously a fellow of the Pacific Institute of Mathematical Sciences and the Killiam Trusts at UBC in the Laboratory of Computational Intelligence in Computer Science. He completed his PhD in machine learning in computer science at University of Toronto. And today, I don't know your title of your talk. So welcome, Ben.
All right, welcome everyone. So we need a slide switch. There we go. All right. So welcome, everyone. So my name is Ben Marlin. As was just mentioned, I'm a faculty member in the Manning College of Information and Computer Sciences at the University of Massachusetts Amherst. I'm going to talk today about uncertainty and adaptive interventions. So this is going to be a talk in the mobile health space. My group works on a number of different things. We work in clinical health, so analysis of electronic health records data. We also work in the mobile health space. I work on embedded machine learning for wearable devices, a range of different things. This talk slot is narrow, so it's not really enough time to talk about lots of different kinds of things, so I decided to do a deep dive into one specific topic. So what I'm going to talk about today, within the context of mobile health, is some work that we've been doing looking at how, in adaptive interventions, machine learning-based context inferences are stacked below methods for learning intervention policies. So the key notions here will be around adaptive interventions, in particular just-in-time adaptive interventions. And this is work that I've done with a number of different collaborators. So Professor Susan Murphy at Harvard, Pedja Klasna at the University of Michigan, Donna Spreitmetz at USC, recently retired, Professor Santosh Kumar at the University of Memphis, my student Karin from UMass Amherst, and I'll talk about a little bit of work from Bonnie Spring as well, from Northwestern. This work has been supported by a number of different center-level programs. So we have an older center, the MD2K Center, that was centered at the University of Memphis. MDOT is a center we have right now. It's an NIH P41 Biotechnology Resource Center. And I'll mention just quickly Massey ITC. It won't feature in the talk today. But Massey ITC is an NIH-funded P30 center, specifically in aging and Alzheimer's disease, with a focus on AI and wearable technologies. So if you're interested in Alzheimer's disease and aging and machine learning and wearable devices, come and talk to me because we have money and we want to give it to you. Right? All right. So in terms of the outline for the talk today, the work I'm going to talk about was presented at UAI just recently. So if you're interested, you can get GitHub details, the QR code here. Because this audience is sort of mixed across different areas of health, I'm going to start by talking about what just-in-time adaptive interventions are. I'm going to talk about sources of state uncertainty in just-in-time adaptive interventions and why this is an important problem. We'll talk about some preliminary work assessing the impact of state uncertainty for these problems, and then I'll conclude. All right, so let's get started. What is a just-in-time adaptive intervention? So just-in-time adaptive interventions are predicated on the idea that through time, the internal and contextual state of a participant, if we're talking about a behavioral trial or a patient, if we're talking about a treatment setting, changes. And the idea is we want to be sensitive to those changes over time when we're looking at how we're intervening. So the notion of a just-in-time adaptive intervention is really one where we're intervening and adapting intensively through time. So this work really has come out of the behavioral science space, as a concept. It's applicable in the more general sort of medical space as well. Some examples of this in the medical space might look like medication titration. So we have a particular medication and we're not sure how to dose it. We want to look at using contextual information, maybe garnered from wearables or from self-report, to allow us to adapt the dosage. So this is relevant for medications where you need to sort of max out the dosage right at the border between therapeutic benefit and toxicity. In the behavioral space, there's lots of examples of these kinds of interventions around things like behavioral nudges. And I'll talk about some specific examples, but in cigarette smoking cessation support, in physical activity promotion, and so on. Okay, so 2 quick examples in those 2 areas. So I'm going to talk first just briefly about some work from Bonnie Spring's group in an intervention called Sense to Stop, which is inside this just-in-time adaptive intervention framing. So Sense to Stop was an adaptive intervention designed to support smoking cessation. There are multiple intervention options consisting of different mobile apps that could be recommended for someone to use. And this is on a momentary basis. So at a given point in time, we might decide that it would be a good idea if you practice some mindfulness. Right? And so the idea is that those decisions are being based on inferences that are coming from data from wearables. So in the case of Sense to Stop, one of the key constructs is a binary stress construct. Are you more likely to be experiencing stress right now or more likely to not be experiencing stress right now? And that's inferred, again, from a collection of wearable devices, in fact, using a machine learning model. Right? And so the decision rule stacks on top of that machine learning-based inference. Here's a second example. So this is a trial called Heart Steps that came out of work with Petja Klassen and Donna Sprotman, who I mentioned earlier. So Heart Steps is a physical activity promotion intervention. It's multi-component, so there are sort of a variety of sort of categorically different kinds of intervention components, but the idea is to improve physical activity and decrease sedentary behavior. So the intervention options include goal setting, planning, and then contextually tailored anti-sedentary and walking suggestion messages. So these are messages that will pop up in an app and ask you to do something, but they're triggered based on a number of context variables that come from different places. So Heart Steps uses location, it uses time of day, it uses weather, and it uses an activity context inference that's provided by Fitbit itself. And of course, under the hood, there are a number of algorithms that support that. Right? So there's a sort of state space here consisting of different variables, including things that are being inferred based on wearable data. So very much in the same vein as Sense to Stop. This is a map of what this process looks like in general. So we have a participant, if we're talking about a treatment scenario. So I'm going to talk about a sort of research study scenario. If we're talking about a treatment scenario, sub-in patient for participant, embedded in some environment. The idea is with our wearables and self-report, we're collecting data in the free living environment. What we really care about for applying these adaptive interventions are decision rules. And those decision rules typically are framed in terms of higher level state concepts, right? So we want to know things like, are you stressed? How much physical activity have you had in the last 30 minutes? And what we have coming in are these lower level data items, right? So maybe we have ECG or we have PPG collected from a smartwatch or from a chest band or something like that as the raw data. And so there's a stack of inferences that need to be made, maybe from raw ECG to heart rate variability to stress, maybe with additional variables coming in on the side. Okay? So fairly sophisticated machine learning-based inference models that fall in the detection sort of space. So we're not trying to predict anything. We're just trying to say right now, what state are you in, right? So that we can condition the decision rule on that state. The decision rule is tasked with selecting between multiple intervention options. So in the messaging space, again, it's not like there's one message where we just say, every time, go take a walk, right? They're contextually tailored messages. So they're looking at what is the weather context, what's the location context, what's the activity context, and selecting between a sort of space of possible messages that could be sent as nudges, right? And so it's not just, are we going to recommend goal setting or are we going to recommend messaging? It's a quite fine-grained tailoring, okay? So like I said, the inferences are machine learning based. Typically, we're going to want to learn these models. We don't know how to get from the raw data to the high-level state that we're interested in. And the decision rules also should be learned. So you can operate a just-in-time adaptive intervention with a static decision rule. The adaptive part refers to adapting to changing context of the participant, not adapting the decision rule itself. But if we use fixed rules derived, let's say, from expert knowledge, we basically have an expert system for the decision component. We'd rather learn over time how to fine-tune these rules or even synthesize them from scratch. Okay? So both components are learning, and then the problem is the way these interventions are typically fielded, you first learn a state inference component, maybe using a lab study or something like that, and then you stack the decision rule on top of it. The inferences are typically hard inferences. So we're going to say, yes, you're stressed. No, you're not stressed. Yes, you're definitely at home. No, you're definitely not at home. And so the obvious problem that arises here is error propagation, right? So there's going to be a lot of uncertainty. The data sources don't give us perfect inferences. And so the question is, what happens when you ignore the state uncertainty and you start stacking these systems together? And then can we do something better than stacking hard inferences when we look at composing these system components to try to maximize therapeutic efficacy? So if you do a bad job at the inference component, it doesn't matter if your decision rule is perfect. You're going to have a suboptimal intervention because you're conditioning on the wrong information. Okay? So to summarize, what I'm going to talk about is how does state uncertainty impact the learning of adaptive intervention decision rules? Right? So if we don't have a fixed rule, we're going to learn it. What happens when we compose these pieces together? So to do that, the first thing I want to talk about is state uncertainty. So what's going on? So we can think about the state that we're conditioning on in these problems as being multivariate. There are lots of different dimensions of state that might be relevant for a particular problem. Some parts of that state we might consider just to be observed. We know what the values are with confidence, maybe with high accuracy. There might be other components that are only partially observed. So we could have missing data. Your wearable runs out of battery. Now we don't know what your heart rate is anymore or your recent step count. What do we do? That's a kind of problem. It might be inferred. So we might have lower level raw data like I was describing, and we're making an inference for a higher level construct. And so it's not actually known, right? At that point, there's an inferential process that's running, some kind of detector or predictor. And then lastly, and sort of most insidiously, there are latent variables, so things we didn't even think that we should have looked at when we were forming the state, right? So these are in the real state, but they're maybe not in the state that we're thinking about when we're designing our decision rules. So all the last three here are different sources of uncertainty for this kind of process. So if we have missing data, partial observability, if we're performing inference and those models are not 100% accurate and confident, then there's uncertainty there. And then, of course, if there are latent variables that we're not even modeling, there's another source of uncertainty there. Okay. So let's talk about state inference uncertainty. This is the most relevant machine learning piece. So this is where we're using detection models to try to make inferences for state variables. So the problem here is really a predictive inference problem. So it's a prediction problem. If we think about the uncertainty decomposition for posterior predictive inference, folks may have seen this before. The uncertainty there decomposes into two pieces that we can think of as allotoric and epistemic uncertainty. The allotoric uncertainty is really about data noise. So if there's noise in the relationship between the targets you're trying to predict and the data that you have, because of measurement error or other things, and it's sort of irreducible in the system that you're looking at, that's a component of the uncertainty. The other piece, the epistemic piece, is about data scarcity. So in mobile health, because we're often looking at novel devices, we're starting from scratch all the time. So we have a new device, we have a new patient population, maybe we have a new condition we're trying to study. We're always in a small data regime, and so we're always in this data scarce condition when new projects are starting. And that's essential, really, to think about the uncertainty in the models that we're stacking together. And of course, as everybody knows, if we only had the allotoric uncertainty and everything else was perfect, you still have like the Bayes error of the detector, right? So that there's going to be irreducible error that results from the uncertainty. And the more different sources of uncertainty we have, the less certain we are about these predictions, the more potential there is for context inference error when we make hard predictions. So if we have a detector and we have to say, yes, you're definitely stressed, or you're definitely not stressed, there's going to be some amount of error in those predictions, and it just depends on what the uncertainty is in the underlying constructs. Okay? All right, so the other piece is the latent variables. And in the behavioral space, there's a ton of these latent variables, right? So there's latent cognitive and affective variables that are maybe the hardest to get at in the mobile health space because they're just very hard to assess. So they're not really things that you can easily get at passively using wearables, and some of these are also really hard to get at using self-report. So these are things that are behavioral processes and cognitive processes that are going on in the participant or the patient's head, but they're hard to get at. They're there, and they have important effects, but they're difficult to elicit or measure. So the first one I'll mention is salience. So salience is a concept that looks at the degree to which a particular stimulus captures an individual's attention. So here, when we think about stimulus, think about an intervention component, for example. So if we're providing some intervention component, how do we tell whether it's something that you're noticing, that you're attending to, and so on. So there's a salience process every time we put something in front of someone, but it's not easy to access, and it's very hard to probe, right? So we can't, if we show you something and then ask you how salient it was, we just primed you to think about the thing we're asking about. Okay, it's like a Heisenberg uncertainty principle. Like you can't ask about salience without affecting salience. Okay, so it's really hard to deal with this kind of process, but it's something that impacts the perception of the interventions. Okay, so there's a couple others. Habituation is maybe somewhat easier to probe. So habituation describes the idea that as time goes on, if we keep doing the same thing, so remember the example I gave where we only have one kind of message and it says, go outside and take a walk. You've been sitting for 30 minutes. Like Fitbit does this for some of the devices, right? It will prompt you routinely with the same message. And the idea is as time goes on, if we keep doing that, people will just start ignoring it, right? So that the effect of the intervention maybe goes down over time. But there are lots of other reasons why the effect of the intervention could be modulated through time, right? So this is maybe more of a disentangling problem than just looking at, does your response to intervention appear to decrease? Engagement is another important construct. So engagement is really, it's a multifaceted thing that has sort of behavioral and cognitive and affective components to it. So it's the degree to which an individual adheres to, applies effort towards, attends to, finds useful an intervention. And so this is, again, one of these variables that can impact someone's experience of an intervention and sort of moderates whether a particular intervention or intervention component might be efficacious for that person. And again, it's hard to probe this. It's multifactorial. Asking questions about it, they're not necessarily reflecting on the intervention components in a way that will allow them to answer this question if you asked it straight out, right? So again, in principle, some of these things are known. Some of them are just, unless you're scanning someone's brain and you have a mapping between their cognitive and affective states in these variables, not something that you can get at easily at all. Okay, so that's sort of a quick overview of what these different forms of uncertainty look like, where they're coming from, right? So there's a machine learning problem around state inference and stacking these components together. Then there's this question, more insidious question of sort of these latent variables that are really hard to measure, and typically people don't ask about them when collecting data. Certainly things you can't get at currently using passive sensing. Okay. So the next piece I want to talk about is some of the methodological work that we've done, looking at the question of assessing the impact of state uncertainty. So as you can imagine, if we're running trials with real people, this is incredibly expensive. To get this off the ground, what we wanted to do is start with some basic simulation studies and look at building an environment that captures some key aspects of the behavioral processes that I just described, built on top of a model based on some of the existing JITIs. So I mentioned heart steps and sense to stop. So we're going to grab some components from those. We're going to grab some of these sort of insidious latent variable constructs that I described. We're going to model an idea of state uncertainty. We're going to put all those pieces together and then probe that system and ask questions about how well are we able to learn policies under ideal conditions when we have some of these uncertain processes sort of running over top of this. Okay? So to start, I'm going to tell you a little bit about the environment that we built, and the GitHub link I put up at the beginning has code for running these environments. If you're interested, it's implemented in OpenAI Gym. So what are the pieces? So as I mentioned, we're going to build this off of heart steps. So the conceptual model here is that it's a physical activity intervention. The outcome we're interested in, the proximal outcome, is going to be around steps. So how many steps are you taking? It's going to be a messaging modeled intervention. So we're going to think about several different types of messages that we could push out that are maybe tailored as well as not tailored, as well as not doing anything. We're going to model a binary stress context, similar to what sense to stop does. Right? So this is modeling our machine learning inference that takes a whole bunch of underlying data and then makes a decision about stress, no stress, or more likely to be stressed, more likely to be not stressed, as an outcome or as an aspect of state. We're going to include two variables that we'll toggle on or off as being latent or not latent. So one is a habituation construct that I'll describe. So as the intervention goes on, the more messages we send to people, we might expect they'll get more habituated, which happens in practice with these kinds of interventions, and respond less to the suggestions. The other is the flip of engagement. So engagement is a positive construct. If people are engaging in the intervention, typically the intervention will have more impact. The reciprocal of engagement is something that we'll call disengagement risk. Disengagement risk is a particular problem in adaptive interventions when you are providing content that is poorly tailored, right? So if I have an intervention and it's conditioning on the weather and it's pouring rain outside and I say, why don't you go outside and take a walk? It's nice and sunny outside, right? And you start to see that the system underlying the intervention is just making completely incorrect recommendations based on what your real context is. People lose confidence in the intervention system, and eventually they'll just start ignoring it, right? So there are lots of different ways that you can fail to contextualize. In this particular example, we're going to look at the stress inference and whether it's correct or incorrect. And again, that's one of the inferences that's maybe a little bit harder to make. So it makes sense to think about that component. Okay, so the way I'll tell you about some of the simulation details. There's lots of details here. I won't go over all of them. The way that the stress context inference simulation works is very straightforward. We won't have any markup structure on the stress state. So we'll call it here the context CT. We're just going to flip a coin, and we'll say it's equally likely to be stress or no stress at every time step. And then we're going to run a little very simple sort of machine learning-based inference on top of this, or statistical inference. So we're going to generate a class conditional feature from a class conditional feature distribution here, just a sample from a normal distribution. So the mean of the normal is either 0 or it's 1. We have a standard deviation parameter that we can set on that that's going to control the uncertainty in that class conditional feature. And then we're going to invert that model and get back a probability over stress. Okay? So the P of CT, P of XT given CT, we just apply Bayes' rule, we can get back P of CT given XT. And we'll call that the probability of stress. Right? And then you can look at the most likely value of that variable. So this is the most likely inference. If we wanted to make a hard inference, typically we would predict the most likely class. And so we'll just argmax over this PCT, okay, to get back a hard indicator. So with this really simple model, we can map out what the relationship is between the uncertainty in the state, which here is the sigma, and then the context inference error. So as the sigma goes up, the amount of uncertainty goes up in that state inference, and the context inference error that you make when making the most likely prediction also goes up. Okay? So there's a couple of different contrasts that we'll make later on, including what if we condition on the most likely state, and then what if we just use the probabilities directly, okay? Something like a weak sort of POM-DP kind of formulation. So we'll come back to the probabilities and the inferences in a bit. In terms of actions, there are 4 actions that we can think about applying. We can not send a message at all, we can send a non-tailored message, or we could try to tailor the message to the context. Okay? So the underlying learning agent here is sort of in a gambling scenario. Okay? They can do nothing, and then you'll have no therapeutic effect. Right? The choice to send a non-tailored message is an interesting one. If we think about the effect of uncertainty, it may be the case that when context uncertainty is high, we shouldn't tailor at all. Okay? We should just do the safe thing and send something non-tailored. Don't make a guess at what the stress is or how to tailor a message. Just back off, right? So this is an interesting aspect of this work when you start thinking about the state uncertainty itself as being part of the state. You don't necessarily have to do the thing that maximizes expected utility. You can have categorically different intervention components that do different things in response to how much uncertainty you think there is right now. Right? And so that's why that particular component is included. And like I said, then we can send tailored messages tailored to different states. In terms of the dynamics overview, so we have these 3 variables we need to look at, the habituation level, disengagement risk level, and the step count that results from different tailoring. And so we can summarize the interaction between the actions and the true context that's shown here. So the message tailoring, we can either do no tailoring, we can send a non-tailored message in case it doesn't matter what the underlying context is. If we send a tailored message, 2 things happen. We either tailored the message correctly to the correct context, or we tailored it incorrectly. We took something for a stress condition, and we gave it in a non-stress condition. Right? So we can think about what happens to the different state variables in response to the tailoring and true context combinations. So for habituation, if we do nothing, then the habituation level sort of decays back down at a given time step. So there's a habituation decrement. Based on the definition of habituation, if we send anything else, habituation is going to increment by some amount. Right? So we applied the stimulus, the response to the intervention maybe goes down. In terms of disengagement risk, there are different ways that you can model this. The 2 that are really important here is the idea that if you incorrectly tailor, we conceptualize disengagement risk increasing. People start to realize that, okay, this intervention system is not very good. It's giving me messages that don't match the real context. Maybe I'm going to be less interested in using this. And if that goes on, eventually you have a disengagement event. So if disengagement risk reaches a particular threshold, people just stop, right? So in the context of a behavioral study, someone will call you up and say, like, I'm done. It's a year-long study, which is what Hard Steps was. I want out now because this is silly. And the same thing is true in a treatment scenario. So your patient might follow some intervention regime for some amount of time, and if this disengagement process maxes out, they're not interested anymore, they stop. Okay? Correctly tailoring messages then causes disengagement risk to go down. Maybe your confidence in the system goes up. Okay, so those are the fundamental dynamics for what we were considering to be the latent variables. And then for the step count, again, if we do nothing, there's going to be some base amount of activity that people get. If we apply a message but it's non-tailored, maybe it's less specific, it's not as interesting, so maybe there's less of a response. If we incorrectly tailor, again, we model this as being a sort of a minimal response to the badly tailored message, maybe the baseline response. And if we correctly tailor, then that's the optimal scenario, and maybe we expect to see a bigger response. So there are questions about what's the relative gap between non-tailored and tailored, how much are we incrementing and decrementing, what is the increment process, is it multiplicative or additive, and so on. So there's lots of details there that I won't go over, but this is the high-level overview of how the dynamics behave, just sort of directionally. Okay? Then in terms of the decision rule learning methods, right? So we have the state, we have the dynamics. We're going to look at reinforcement learning methods on top of this process and think about how can we optimize the decision rules, so the selection of the actions based on the context. And we'll look at a couple of different approaches. So in the sort of space of state action value function methods, we'll look at deep Q learning. We're specifically using a dueling double DQN. The details aren't really that important. These models, though, use neural network-based underlying components. So the dueling DQN has a 2 hidden layer MLP as its underlying model. We optimize the hyperparameters of this with respect to the reinforcement learning process. So that is the sort of state action value function is this 2-layer MLP. The other method we look at is reinforce. So reinforce is an example of a policy gradient method. We're using just basic vanilla policy gradient here. Again, with the 1 hidden layer MLP, it turned out to be optimal, whereas for the deep Q learning 2 layers turned out to be optimal, and the details are not the most important. The important thing here with these two is that they do things directly learning to make policy choices based on states are 2 very different processes. They behave similarly in cases where you have no you have linear underlying networks. So if you have a sort of tabular Q learning and you have reinforced with we have underlying continuous state variables, and so we need these nonlinear function approximations. Should perform differently in different scenarios. Reinforce should have better performance. Q learning based method. Stops if the disengagement risk. Disengagement risk goes between 0 and 1. When it gets to 1, the episode stops, and we model the person no longer engaging in the intervention. They get no more therapeutic efficacy from whatever you're trying to do. They stop paying attention. Okay. We run the learning algorithms to convergence. So this is really like a limit study. We're asking the question, if we have some level of state uncertainty, we have some level of inclusion of latent variables, what's the limiting behavior of the ability to learn policy? So forget how, maybe we imagine that we have exactly the same person and we can do unlimited, episodes of reinforcement learning over those same people. How do these algorithms behave? So that's not a realistic setting. In general, you can't do the same intervention to the same person twice, the classic causal inference problem. So the results I'm going to show you, you should think of as the best possible performance you could get out of these algorithms. And in practice, the performance is going to be worse than this, and the decays as a function of uncertainty are going to be worse than this. Right? So this is sort of characterizing the best possible results that you could get. So the first thing I'm going to show you here is the influence of the context inference error rate. So remember, the uncertainty drives the error. The horizontal axis here is the error rate from 0% to 40%. The performance is in terms of total return. There's a test scenario where once we learn a policy, we apply it for 100 random restarts to look at how well the policy does. And so we can look at for every context inference error rate, what is the average total return of the policies. And so you can see that if there's no context inference error, we're getting about 3,000 steps a day, the way that this was characterized out of our intervention scenario. And as the context inference error goes up, the performance drops off. And this is largely caused by disengagement risk exceeding the threshold and then causing the entire learning sort of process to stop, the intervention process to stop. So the left-hand side is the DQN, the right-hand side is reinforce. They're both decreasing as a function of the amount of context inference error that we have. Okay? So this is conditioning on hard context inferences. We can also use context inference probability. So because we have neural networks in these models, we can sort of do whatever we want with them. We can plug in whatever state we want. So we can take the hard inference that we were using, which is what people are using in practice right now. They're using the hard binary states. We can take it out and just put the probability vector right in and learn with that instead. Right? So the blue lines here are showing a different scenario where we use context inference probabilities instead of the hard context inferences, and we let the neural network model propagate the uncertainty forward through the reinforcement learning process to the output side. And so you can see here that just switching from using hard inferences to conditioning on context inference probabilities preserves more of the reward, so higher total return, as the context inference error rate increases. So we get some buffering to the increasing context inference error just by switching this representation. So if we had a probabilistic classifier and we were thresholding it and using the hard value, we could just change it and use the probabilities directly and get a performance boost without doing anything else. This is what the results suggest. The next thing I want to show you is the effect of the latent variables. And this is pretty stark. So the right-hand side, we're looking at reinforce versus the DQN. When we're using hard inferences, okay, so the L here is the most likely context. The right is reinforce versus DQN using the probabilities. And what we've done is remove access to the disengagement risk and the habituation. So in the previous is important. In the previous slide, we're assuming we can see the disengagement risk level and the habituation risk level, right, that they're available to us. So what we've changed here, we swapped from assuming that we can see those variables to making them latent, which is what would happen in practice. And so you can see here the pink line is reinforced and the bluish line here is the DQN. And as the theory suggests, the DQN performance drops rapidly when you introduce these important latent variables. Again, the theory sort of suggested this would happen. The question is, what's the magnitude of the effect? So reinforce is much better. If you compare the two, it's a little bit tricky, but if you compare the two slides to each other, if you look at reinforce on the left-hand side, it starts at about 3,200 and drops down to about 1,200. The performance for reinforce is largely conserved with the introduction of these latent variables, whereas the DQN completely tanks in terms of performance. Right? So we expected this effect. The question was, how big would it be? And the answer is it's pretty big. Obviously, there are a whole bunch of simulation parameters underlying this. And as you change those parameter values, different things can happen. These effects can go up and down in magnitude. And again, the paper completely characterizes what this looks like over a broad swath of sort of hyperparameters for the environment. And these effects are pretty robust. So the sort of directional differences I'm showing you here hold up over a wide range of sort of environment hyperparameter settings. Okay, so that's what I have to tell you. To conclude, the high context inference uncertainty that we've seen and that exists in some of these problems leads to high context inference error if we're performing a hard prediction. And this can cause the performance of learned policies to degrade quickly. The first result that I showed you suggested that if we can use probabilities instead of hard context inferences, we can preserve better performance for longer. Again, in the RL literature, there's lots of literature on what to do when you have uncertainty in your MDP. You can build POM-DPs. There are lots of things that you can do in that space. This is a particularly inexpensive way of taking some of that uncertainty and propagating it through to the decision rule learning process that would be suitable for something like this, where you have to maybe continuously optimize your models as the intervention process runs. The last note here is this question with latent variables, this problem that I mentioned as being quite insidious, can have a large impact. So if there are important latent variables that we're not modeling, you have to be really careful about what kinds of algorithms you're using because there can be large performance differences. It turns out that the reinforce algorithm is much less efficient in terms of episode count to get to a particular solution. So I said we're going to run things out to convergence. The Q-learning methods here make like 10 times faster than the reinforced methods. So the reinforced methods are completely unrealistic for a real-world application, but it highlights a difference between what is achievable using different kinds of RL approaches. So this notion of trying to deal with latent variables in a robust way is something that's really important in these kinds of methods. So in real-world adaptation methods right now, people are using methods like Thompson sampling, if folks know those, that are much more straightforward than some of the methods that I mentioned here. But they have similar kinds of issues. So the latent variables, in this case, are creating interesting delayed effects. You can model those in different ways, and that's some of the things that we're working on right now. Right. So that's it. Thank you very much. And I guess we're deferring. Thank you. We're deferring questions until the discussion phase. So I will exit the stage, and the next speaker will come out. So thank you very much.